This is a comprehensive manual for using sockets in Python. Networking involves linking devices together to share information. Sockets play a crucial role in ensuring effective communication between devices on both local and global networks, as well as between processes on a single device. They serve as a fundamental building block for transmitting messages between devices and allow for precise control over the data being sent or received. This means that the basic structure of this system allows for the creation of highly efficient channels for communication or specialized protocols that do not have the excess baggage that can be found in traditional protocols that are built on socket communication. Essentially, the simplicity of this system allows for more efficient and customized communication methods. Sockets are extremely valuable in client-server applications that rely on immediate communication or handle large amounts of data. This video teaches the fundamentals of socket programming and walks through the process of building client and server applications using Python. Let's get started. Networking is a fundamental concept in computer technology. It refers to the communication between two or more devices or systems to share data, information, and resources. This can be achieved through various methods, such as wired or wireless connections. In simpler terms, networking enables different devices to connect and communicate with each other, allowing for efficient data sharing and collaboration. Networking facilitates the sharing and exchanging of communication and information between devices. By connecting two or more devices together, they are able to communicate and share data. A group of connected devices is referred to as a network. There are various networks in the real world, such as airline and power line networks, and cities connected by highways. These are examples of how different things are connected to each other physically. Just like how there are many types of networks in information technology, the most popular and well-known one is the Internet. The Internet is a global network that connects many different devices and is probably the one you are currently using to read this article. The Internet is made up of various networks that can vary in size and characteristics. One type of network is a local area network, LAN, which connects computers that are close together. These networks can be found in businesses, institutions, and even in homes where devices are connected to a router. There are different types of networks, such as PANs, MANs, and WANs. PANs are small networks, like when you connect your phone to your laptop using Bluetooth. MANs cover a larger area, like an entire city, and can connect devices together. WANs are even larger, covering entire countries or the entire world. The Internet is the biggest WAN network. This text is saying that computer networks are complicated and have many parts. One of the most important parts is a communication protocol. Communication protocols outline the guidelines for transferring and receiving information in a specific manner. These protocols are organized into a system to oversee the different steps involved in network communication. Essentially, certain protocols govern the actions of hardware in terms of receiving, sending, and delivering packets, while others pertain to more advanced aspects such as application-level communication. Commonly used and widely known network communication protocols include, or wireless network refers to a type of wireless communication technology that allows electronic devices to connect to the Internet or communicate with each other without the need for physical wired connections. This passage explains that Wi-Fi, also known as wireless network, is a form of wireless communication that enables electronic devices to connect to the Internet or communicate with each other without using physical wires. Link layer protocols are protocols that operate in close proximity to hardware and are responsible for transmitting data between devices in a wireless setting. It is a set of rules that governs the sending and receiving of data packets on the Internet. IP, also known as the Internet Protocol, consists of a series of regulations that control the transmission and reception of data packets within the Internet. The primary function of IP, a network layer protocol, is handling packet routing and addressing in a network. Is a network protocol used for establishing and maintaining reliable communication between devices. TCP, also known as Transmission Control Protocol, is a method used in networking to create and sustain dependable communication among devices. This is a dependable transport layer protocol that establishes a connection and allows for two-way communication while guaranteeing that data is safe and successfully delivered. It is responsible for managing connections, identifying errors, and regulating the flow of information. Is a connectionless protocol used for transmitting data. UDP is a type of protocol that does not require a connection and is commonly used for sending data. UDP, or User Datagram Protocol, is a member of the same protocol suite as TCP. However, UDP is known for its simplicity and speed, but it is also considered an unreliable connectionless protocol. Unlike TCP, UDP does not conduct delivery checks and operates under the principle of fire and forget. Similar to TCP, UDP is also a transport layer protocol. The Hypertext Transfer Protocol, HTTP, is a protocol for accessing and transmitting information on the World Wide Web, WWW. HTTP, short for Hypertext Transfer Protocol, is a method used to access and transmit data on the World Wide Web, WWW. HTTP is a widely used application layer protocol for communication between web browsers and servers. It is the primary protocol used for serving websites. In fact, the article you are currently reading was also transmitted using HTTP. This protocol utilizes TCP and handles the exchange of information essential for web applications, such as headers for transferring metadata and cookies, and various HTTP methods, including GET, POST, DELETE, and UPDATE. Is a messaging protocol that provides a lightweight method of communicating between devices. MQTT, also known as Message Queue Telemetry Transport, is a communication protocol that facilitates efficient messaging between devices in a lightweight manner. MQTT is a messaging protocol commonly utilized in IoT, Internet of Things, for devices that have limited processing capabilities and rely on battery power. This can include devices such as gas sensors at a mining site or even a smart light bulb in a home. The protocol is particularly beneficial for these devices as it is designed with built-in mechanisms that prioritize reliability even in unstable network conditions. An interesting aspect to note is that although these protocols all utilize sockets in their operation, they also have their own specific functionalities and data processing methods in order to function effectively. This is due to the fact that sockets serve as a fundamental interface for network communication on modern devices, as will be further discussed in the following section. What is the concept of sockets, and why are they important? The meaning and significance of sockets. Sockets are a fundamental communication method that allows for two devices to establish a connection and exchange data. This two-way communication facilitates data exchange between computers, servers, and other network devices. The concept of sockets is essential in enabling data transfer across various networks, making them a crucial component in modern communication systems. In other words, comprehending sockets and their role is crucial in understanding the complexities of network communications. What does the term socket mean? A socket serves as a bridge between various processes on either the same or different machines, referred to as network sockets in the latter case. They act as a layer of separation for connection management and can be thought of as handlers for connections. In Unix systems, sockets function as files and facilitate the transfer of data over the network through the same read and write operations. A socket in either a listening or connecting state is always associated with both an IP address and a port number, which identify the host and process respectively. How do socket connections operate? Sockets have the capability to either listen for incoming connections or initiate outbound connections themselves. When a connection is established, the listening socket, also known as the server socket, becomes bound to the IP address and port of the connecting side. Alternatively, a new socket can be created, which is then bound to both the IP addresses and port numbers of the listener and the requester. This allows two connected sockets on different machines to recognize and communicate with each other without interrupting the listening socket, which continues to wait for other connections. When the connecting socket, or client socket, initiates a connection, it automatically becomes bound to the device's IP address and a freely accessible port number. Upon establishing the connection, this socket is then bound to the other side's IP address and port, using a similar process as the listening socket, but without creating a new socket. In the realm of network systems, sockets refer to communication points used for transferring data between devices. In this tutorial, our focus is not on implementing sockets, but on understanding their role in networks. A socket can be defined as a connection endpoint which links a host machine's IP address and a specific port for a particular application to the IP address and port of the application running on another machine with which it is connected. The concept of socket programming is a way to establish a communication channel between two computers or processes. Socket programming is a technique used to create a means of communication between two computers or processes. Socket programming involves creating socket objects in our code and using specific methods such as listen, connect, receive, and send to manipulate them. These sockets act as unique objects within our program, equipped with special capabilities for working with network connections and traffic. Behind the scenes, these methods communicate with the operating system kernel, specifically the network stack, which is responsible for handling network operations. Client-server communication involves the use of sockets. Sockets play a crucial role in enabling client-server communication. Sockets are an essential component of client-server communication. They facilitate connections and act as handlers for these connections. When sending or receiving data on the web, you establish a connection using sockets. In this scenario, either you or the party you are trying to connect to takes on the role of the server, while the other acts as the client. The server listens for new connections through a listening socket, establishes them, receives the client's requests, and sends back the requested data in its response. The client creates a socket that identifies the IP address and port of the server it wants to connect to, initiates the connection, sends its request to the server, and receives the data in response. This seamless exchange of information between the client and server sockets is fundamental to the functioning of various network applications. Sockets serve as a foundation for network protocols. Sockets act as the building blocks of network protocols. Sockets act as a foundation, allowing for the implementation of different protocols. Popular examples include UDP and TCP, both of which have been previously mentioned. Sockets utilizing either of these transport protocols are referred to as UDP or TCP sockets, are used to establish communication between processes on different computers. IPC sockets are utilized for setting up communication between processes running on distinct computers. Besides network sockets, there are also other varieties, such as IPC, inter-process communication sockets. IPC sockets are specifically designed for exchanging data between processes on the same computer, while network sockets are capable of doing the same over a network. One advantage of IPC sockets is their ability to bypass much of the burdensome process of constructing packets and determining routes for data transmission. Since communication via IPC sockets is limited to local processes, it generally has a faster response time. Unix sockets are a form of inter-process communication in the Unix operating system that allow processes to exchange data locally without the need for a network connection. An excellent illustration of IPC sockets is found in Unix sockets, which, in the Unix system, are simply files stored in the file system. Unlike traditional sockets, which are identified by an IP address and port number, Unix sockets are distinguished by their location in the file system. IPC sockets are known as network sockets. If both the server and receiver are located on the local host with an IP address of 127.0.0.1, it is possible to use network sockets for communication between processes. However, this may add some delay due to the processing of data by the network stack. On the other hand, using network sockets eliminates the need to be concerned about the underlying operating system, as they are universally available and functional on all systems. Unlike IPC sockets, which are limited to specific OS or OS families. Python socket server implementation. Python has the capability to create a server using sockets. A socket server can be built in Python by utilizing its socket functionality. Let's begin by designing a socket server, specifically using Python's TCP server, as it will be interacting with TCP sockets, as we will observe. To avoid confusion, although all servers utilize sockets to establish network connections, we will refer to this as a socket server due to our implementation of socket programming in this example. Code making a Python file that includes standard code in its beginning stages. Generate a server.py file and import the socket module in your Python script. A function named runServer will be included to contain the majority of our code. When adding code to this function, be sure to indent it correctly. The socket object is created in runServer by using the socket.socket function. The IP address family for IPv4 can be specified with the first argument, socket.afinet. Other options include AFINET6 for IPv6 family and AFUNIX for Unix sockets. The second argument, socket.sockstream, indicates the use of a TCP socket, ensuring a reliable connection with in-order data delivery, error discovery and retransmission, and flow control. There is also an option for a UDP socket, socket.sockdgram, which has all the features of UDP. For a more low-level approach, the socket.raw socket value can be used as the second argument to build a custom transport layer protocol on top of the TCP IP network layer protocol. In this case, the operating system will not handle any higher-level protocol features and must be implemented by the user, such as headers, connection confirmation, and retransmission. Creating a connection between a server and an IP address and port number involves specifying the hostname or server IP and port that will determine where the server can be accessed and where it will accept incoming connections. In this scenario, the server is listening on the computer it is running on, which is represented by the variable server IP set to 127.0.1, also known as localhost. The variable port is set to 8000, which is the number allocated by the operating system to identify the server application. It is recommended to use port numbers higher than 1023 to avoid clashes with ports used by system processes. Prepare the socket for incoming connections by binding it to the specific IP address and port that we previously designated. To receive incoming client connections, the server socket needs to be in a listening state. This can be achieved by using the listen function. The argument backlog specifies the maximum number of unaccepted connections that can be queued. The value 0 is used in this example, allowing only one client to interact with the server at a time. If the server is already busy with a client and receives a connection request from another client, it will reject the request. A larger value for backlog, such as 1, indicates how many clients can be in the queue before the accept method is called on them. This means that when the server calls accept, the client is removed from the queue and can start communicating with the server. If multiple clients are in the queue, the first one will be accepted first, and the others will wait until the server is free. The backlog argument controls the size of the queue. By default, this value is set to the system's default. which can be viewed in the process.net/sym file on Unix systems. To receive and process incoming connections, we first use the accept method, which pauses the execution thread until a client is connected. This method returns a pair of values, con address, where con is a new socket that is connected to the client and can be used for communication, and address is a tuple containing the client's IP address and port. Instead of using the initial listening socket, referred to as server in our example, to communicate with the client, a new socket is created. This is because the listening socket must remain available for incoming connections from other clients. In our current scenario, we are only handling one client and ignoring any other connections, but this becomes more important in a multi-threaded server setup. Establishing communication cycle. After a successful connection with the client is established using the accept method, we begin a continuous cycle of communication. Within this cycle, we use the receive method of the client socket object to retrieve the specified number of bytes from the client, which in this case is 1024. This size is commonly used as it is a power of 2, making it potentially more optimized compared to an arbitrary value. However, you may change this size as desired. The data received from the client is in binary form, and we use the decode function to transform it into a string. If the received message is the word close, the communication loop is terminated, and a confirmation is sent back to the client before ending the connection. Otherwise, we print the received message to the console. The confirmation, in this case, is simply a string of closed sent to the client. It's worth noting that we use the lower method on the received message in the if statement to ensure it can handle both uppercase and lowercase characters. After receiving a request from the client, we need to ensure that the server responds correctly, unless the client wants to end the connection. In the while loop, directly after printing the received request, we can add the following lines. They will convert the response string, in this case accepted, into bytes and send it back to the client. This ensures that whenever the server receives a message that is not close from the client, it will automatically respond with the accepted message. After successfully exiting the infinite while loop, we can now release the resources utilized for communication with the client. In order to do so, we call the close method to close the client socket. This ensures that the system resources allocated for the communication process are freed up. Similarly, we also close the server socket using the same method. This effectively shuts down our server. However, in a real-world scenario, our server would typically continue to listen for incoming clients rather than shutting down after communicating with just one. But don't worry, we will explore another example later on. For now, we can add the following lines after the infinite while loop. To create a client socket in Python, you must first establish a server and then proceed to build a client that can connect and make requests to that server. The steps are outlined below. 1. Begin by creating a Python file with appropriate boilerplate. 2. Name the file client.py. 3. Import the socket library into this file. The run client function is where all of our code will be contained. Creating a TCP socket object is the next step, following the instantiation process. This socket object serves as the client's channel for communicating with the server. To establish a connection to the server, you must provide the correct IP address and port number. This should correspond with the IP address and port previously assigned in the server.py file. Firstly, we will establish a connection to the server by utilizing the client socket object's connect method. It is important to mention that we have not assigned a specific IP address or port for the client socket. This is a standard practice for clients, as the connect method will automatically choose an available port and select the optimal IP address from the system's network interfaces, in this case being 127.0.0.1, and bind the client socket to them. Once a connection has been established, we initiate a continuous communication loop to transmit several messages to the server. Input is received from the user using the input function in Python, which is then converted to bytes and limited to a maximum of 1024 bytes. The message is then sent to the server using the client.send function. When the server receives a message from the client, it will send a response back. In our client code, we need to be able to receive and handle the server's response. To do this, we use the receive method in the communication loop to read a maximum of 1024 bytes. The response is then decoded from bytes into a string, and we check if it is equal to the value closed. If it is, we exit the loop, which will end the connection between the client and server. If the response is not closed, we print it to the console. The client socket connection should be closed by using the close method after the while loop in order to release resources and terminate the connection. This will occur when the closed message is received and the while loop is exited. Dealing with numerous clients, concurrent computing, collaborating with multiple clients simultaneously, parallel processing, managing multiple clients concurrently, multi-threaded operations, handling various clients at once, simultaneous execution, In the previous instance, we explored how a server responds to requests from just one client. However, in real-world scenarios, multiple clients may need to connect to a single server concurrently. This is where the concept of multi-threading comes into play. Multi-threading is used when there is a need to simultaneously handle multiple tasks, such as executing multiple functions. This is achieved by creating separate threads within a single process, where each thread contains a unique set of instructions that can be processed by the processor. Compared to processes, threads are more efficient and require fewer resources as they exist within a process. The limitations of using multi-threading in Python should be noted. This is because the standard implementation of Python, CPython, is unable to run multiple threads concurrently. This is due to the global interpreter lock, ZIL, which restricts only one thread from executing at a time. Although this is a different subject and will not be discussed, for our example, it is sufficient to use limited CPython threads in order to convey the message. However, in a practical setting, if you are working with Python, it would be beneficial to explore asynchronous programming. This will not be discussed now, as it is a separate topic and often involves abstracting away lower-level socket operations, which is the main focus of this video. Developing a server function that creates new threads. To utilize both sockets and threads, ensure you import the socket and threading modules in your Python file. The run server function can be defined as follows. First, a server socket is created, bound, and set to listen for incoming connections, similar to the example provided. This function then enters an infinite while loop, constantly accepting new connections. Each time a connection is accepted, a new thread is created using the thread constructor. This thread will run the handle client function, which we will define later, and will pass the client socket and address as arguments. The address tuple contains the connected client's IP address and port. Once the thread is created, it is started to begin execution. It is important to note that the accept call is a blocking function, meaning that on the first iteration of the while loop, the program will stop and wait for a client connection before proceeding with any other tasks. Once a client does connect, the accept method will return, and the program will continue by spawning a thread to handle the client before going back to the beginning of the loop and waiting for another connection. Finally, the function includes error handling to ensure that the server socket is always closed in case of any unexpected issues. One way to create a client handling function that runs in a separate thread is to define a function called handleClient above the run server function. This function will run in a separate thread for each client's connection and will take the client's socket object and adder tuple as arguments. In this function, the same steps as in a single-threaded example are followed, with the addition of error handling. A loop is started to receive messages from the client using recv, and then a check is made to see if a close message was received. If so, a response of closed is sent, and the connection is closed by breaking out of the loop. If the message is not a close message, the client's request string is printed to the console, and the loop continues to receive the next message from the client. At the end of the function, error handling is included for unexpected cases using an accept clause, and a finally clause is used to release the client socket using close. This ensures that the client socket is always properly released, as the finally clause will always be executed. For a client to handle errors, we can use the same client implementation as shown in the first basic examples to establish a connection. However, if we want to add some more robustness, we can slightly modify the code by implementing try-except blocks. This will allow for better error handling. The code below is similar to the previous client example, but includes these try-except blocks.